Hi guys, welcome back to the next lecture. Today we will discuss the concept and definition of normal spaces, and we will also discuss some basic properties of normal spaces. So the concept of the normal space, it means it is the concept of a length of vectors in a generalized vector space. Okay, so a norm generalizes the concept of the length of the vectors in an arbitrary vector space. Okay, so basically a normal space is a vector space. So we will give the definition of what is meant by a norm. Okay, so normal space is a vector space with a norm defined on it. So first we will define what is meant by a norm. Okay, so suppose x be a linear space over k, where k may be real or complex, then a norm on this linear space x is a function which is a real valued function, okay, such that for all x y belongs to x and k belongs to x, it satisfies some the following properties. Okay, the first property is norm x greater than or equal to 0. It means it cannot be a negative quantity. Okay, second property is norm x equal to 0 if and only if x is equal to 0. Third property, norm x plus y, which is less than or equal to norm x plus norm y, which is known as triangular inequality. And the last one, norm kx equal to mod k into norm x. Here, k may be uh, real or complex. So if these four properties are satisfied, then we say that space x, a linear space x together with this norm is called normal space, and its notation is like this: x space x and with a norm defined on it. Okay, now if we introduce dxy as the norm of x minus y, where x and y are any arbitrary elements of x, then we can easily see that dxy satisfy all the properties of matrix. Okay, that is dxy is always greater than or equal to 0, because dxy equal to, we have defined dxy equal to norm x minus y. We know that norm of x minus y, which is always greater than or equal to 0, which is non-negative. Okay, and the second condition, if dxy equal to 0, that means norm of x minus y equal to 0. Okay, so this implies x minus y equal to 0. That means x is equal to y. And the third condition is dxy equal to, we have defined dxy equal to norm x minus y. Okay, so here we interchange x and y, and we write like this and taking minus 1 outside. Then by using the property of norm, we can write this as mod minus 1 into norm y minus x. So mod minus 1 is 1 and norm y minus x is equal to dyx. Okay, so we can write dxy equal to dyx. And the last property, dxy can be written as norm x minus y, which is, we know that by using the triangle inequality, we can introduce another element z in x. So we can write then norm x, which is less than or equal to norm x minus y, z plus norm z minus y. Okay, so that means dxz plus dzy. So dxy less than or equal to dxz plus dzy for all x, y, z belongs to x. Okay, so the properties of the matrices are satisfied as soon as we introduce the concept of the metric in terms of norm, and this gives a metric. Okay, so here x together with this metric d is a metric space. Okay, now so it means every normal space is a metric space, because whenever we take a norm, it can be converted to a metric. Okay, but the converse need not be true in general. That is, every normed space is a metric space, but converse need not be true in general. For example, if we take the set S as set of all sequences of real or complex numbers, here the sequence may be bounded or unbounded. Okay, and we define dxy as like this: summation I varies from 1 to infinity 1 by 2 raised to I into mod xi minus yi divided by 1 plus mod xi minus yi. Okay, where x and y are belong to this S, where x, here x is in the form that is x sequence xi I varies from 1 to infinity, and also y equal to yi I varies from 1 to infinity. Okay, then we can easily shown that this S together with this metric is a metric space. Okay, but if we define dxy as norm x minus y, okay, and we fix y equal to 0, that means dxy, then we can get norm x only. Okay, and then our definition becomes summation I varies from 1 to infinity 1 by 2 raised to I mod xi divided by 1 plus mod xi. Okay, and we multiply our x by a field element k, then mod norm kx, that means summation I varies from 1 to infinity 1 by 2 raised to I mod kxi divided by 1 plus mod kxi. So from there we cannot take k outside. That means the fourth property of the norm cannot be satisfied. We cannot take this k outside. Okay, and therefore we can conclude that the converse need not be true in general. That is, every metric space need not be a normed space. Okay, now we will look at some other properties. That is, the function norm is uniformly continuous. We can easily prove this. Let xy belongs to x, then norm x is equal to norm x can be written as norm of x minus y plus y, which is less than or equal to norm x minus y plus norm y. Okay, then that is, if we take this norm y from right side to left side, then norm x minus norm y less than or equal to norm of x minus y. This is our first equation. Then similarly we can write norm y as like this. Okay, then also norm x minus norm y, which is greater than or equal to minus of norm y minus x. Okay, so that is, or we can write minus of norm y minus x, which is less than or equal to norm x minus norm y. So this is our second equation. So from 1 and 2 we can write minus norm y minus x, which is less than or equal to norm x minus norm y, which is less than or equal to norm x minus y. Okay, so that is modulus norm x minus norm y, which is less than or equal to norm x minus y. So by Lipschitz condition, we can say that norm is uniformly continuous on x. Okay, another property of norm is continuity of addition. Okay, suppose we have xn converges to x and yn converges to y in x, and also kn converges to k in k, then xn plus yn converges to x plus y in x. The proof is very simple. If we take norm xn plus yn minus if we take norm xn plus yn minus x plus y, which can be written as norm xn minus x plus norm yn minus y. We know that xn converges to x, so that means norm xn minus x converges to 0, and also norm yn minus y also converges to 0. That means the total converges to 0. Okay, that means norm, that means xn plus yn converges to x plus y. Okay, similarly we can show that continuity of scalar multiplication, that is if xn converges to x in x and kn converges to k in k, then kn xn converges to kx in x. Okay, proof. We can write norm kn xn minus kx as norm of kn xn minus knx plus knx minus kx. Okay, then we split this norm, then which is less than or equal to norm kn of xn minus x plus norm of x kn minus k. Okay, we take n outside and also kn minus k. Okay, so this becomes which is equal to mod kn into norm xn minus x plus norm x into mod kn minus k. This is the fourth property of norm. Okay, then so this converges to 0. Okay, given that xn converges to x. Okay, so that means this converges to 0, also kn converges to k. So both of these two terms are converges to 0. This means totally converges to 0. So this shows that kn xn converges to kx in x. Okay.